Just to summarize a bit what we've done so far. So we've seen up to exercise 4. I will now go on to these 2 additional exercises before talking about point-to-point communication. So after doing exercise 6, I will go back a bit in the slides, and then we come back and do these 2 exercises. So I think so far we've been looking at relatively simple examples. So we completed exercise 4. I just want to say a few words about this before we move on. So something that I didn't really reveal, maybe deserves talking about a bit, is that, okay, in the scatter operation, we have, remind you what we said. So we have a file which has 8 lines, and we have 8 processes, and each process gets 1 line of this file scattered from the root process. So this is a very narrow use case, right? So in principle, I should have checked things like, are there indeed the same number of elements, the same number of processes as there are a number of elements in the file, because things can go wrong if you now go and try and run this with more than 8 processes, right? Because there are not enough lines in the file, etc. So I should have done more checks somewhere here, for example, if this would have been a careful, foolproof code, but I didn't. So I just want to let you know that for the sake of simplicity of this exercise, a lot of things have been simplified and assumptions have been made about the number of processes and the number of elements in the file being the same. Okay, so now I'll go to exercise 5. Right, so this is exercise 5, where this exercise demonstrates the gather operation. So it starts like exercise 4, in which the root process reads the 8 values from the data.txt file and then stores them in this array. And then what we want to do is we want, again, the elements to be scattered, 1 element to each of the 8 processes. But then we want each process to divide its elements divided by 2, and then send it back to the root process. Okay, so what we're simulating a sort of, we're simulating an operation in which the root process distributes some work to the other processes and then collects back the result, right? The work that we're doing here is very simple. It's dividing each element of this array by 2, and this is delegated to the processes. So it's a bit simplified here for the purposes of this exercise, but you can imagine how this can maybe map to a more complicated problem maybe that you have, right? So we're reading, so one process reads the data from a file. It wants to do some processing on this data, so it distributes it to the processes. Each one does this processing of the elements on a subset that corresponds to that process, and then the root process collects back the results, right? So this is what it looks like in that file now. If you look at the main part of it, so there's a scatter operation that you should copy from exercise 4, as we showed in the previous exercise. Then everybody just divides their number by 2, so it multiplies by 1/2. And then there's a gather operation that you need to fill in so that the root process collects everything. And so in the end, the root process prints all the elements of the variable. So just rank 0 does this, right? And what you should see is that now the elements of this array are half of what was in data.txt. And yeah, that's what you should see. So it should look like this. And of course, now this is all in order because this is just done by a single process, right? So notice that the other processes never need to have all the elements, right? They only need to have their single element. It is only rank 0 that ever needs to have allocated this array bars. So let me open this. Where are we? Run window. So right. So this is how I said it. It begins like exercise 4. You're supposed to complete the scatter operation to distribute the elements of the processes, and then the gather operation to bring back the different variables, which are now been divided by 2 by each process, back to the root process, which will print them. Okay. I'll give you 10 minutes for this. So we come back a little bit less than 10 minutes. So we come back at 45 past and do the solution. So just a quick reminder what we said before. If you don't remember the arguments, you can always use man, which stands for manual, and then the MPI function name. And this is just to quickly see what the order of the arguments is, if you don't want to scroll back to the slides.
Hello, Yanis.
Mm-hmm.
What are we doing
Yes.
now? Exercise 5?
5, yes. I have until 45 past to solve this.
Thanks.
Would you like me to repeat something?
Yeah, if I missed what we were doing. Yeah.
The whole thing? Yeah, so well, okay, I can say it again. So as I said, this exercise begins like exercise 4. So there's 8 elements in data.txt. And the idea is that each process, that the root process, will read all the 8 lines again, just like in the case of exercise 4. And then the elements will be scattered, one element each to the processes, just like in exercise 4. But now each process will divide its element by 2, and then we want to gather them back into vars of the root process. So scatter the elements to the processes, each process divides by 2, and then gather them back to the root process. And then the root process will print them out so you can confirm that this is actually indeed happened as you expected it to. So what I said is this is simulating a kind of situation where you want one process to read in some data, distribute the data to the processes, they do some processing, and then they send it back to the root processes, which collects it into a bigger array.
Okay, thanks.
Just going to close the window because there's some background noise. Okay, So let's take a look at this. So the scatter operation will be the same as before, right? So it'll be something like, I just copied it from before. Oops. So send count is 1 because each rank will take one element. Receive count is 1. Put it in the scalar variable var, and they're both double, and the root process is 0. Then each process will divide the variable it got by 2, and then we need to fit in the gather operation. Let's see what the order is. So first is the send buffer and the send count, and then it's the receive buffer and the receive count types. So the send buffer is of course now going to be the scalar variable. And what we want to do is put it back in the original vars array because we don't need to allocate more space for that. We want to put it back in the root process. This could have gone at any process, by the way, just as long as you actually use that one to print at the end. And I think there's only the typo, that should be correct. So again, we compile, we submit. We'll wait a bit. And now I should be able to see in the output, this should be half. Each element should be half of what's in data.txt. Yeah, looks good. Okay. Right. Any questions with that? I guess it's clear then. So we scattered an array that we read on the root process was scattered to the available processes. Then each one did the same operation on this, and then this was scattered back. And if this is a very cheap operation, as I said, but one can imagine a very expensive operation going on here, which means that you take advantage of the fact that you have now more process to do this, right? Because if you would do this only on one process, then you would have to loop over the 8 elements and divide each one by 2, one at a time, if you only had one process, right? But now you have one process per element. Okay, so let's move on to exercise 6. And this demonstrates a reduction operation. Now you have this data.txt file, which has many more elements than before. It has 2,520 random numbers, 1 per line, okay? So NLMs equals 2520. What we want to do is we want to sum the elements of this file. I'll just do this here, but just to convince you that there's a lot of numbers in here, and I type Q, then I come out of this, and this command will count the lines just to ensure that indeed there are as many as I say in the slides, 2,520 lines in data.txt, okay? So now what I want to do, as I said, is I want to sum the elements of this file. So what I want to do, actually, the way I want to do it is the root process to read all elements into an array called vars. And then I want the elements to be scattered to all processes. And I want to dynamically determine how many elements each process will receive. So I know what the number of processes is. I gave the number of elements, I hard coded it into exercise 06.c. Let me just show you. So I have hard coded NLMs, so the number of lines in the file to be 2,520. And what I would like to do now is, after I scatter, let me go back. Yeah. So after these scattered the elements to all processes, I want each process, right, to sum its local elements. So not the, you know, the subset of the elements that correspond to that rank, and then use a reduction operation, use this Mpi Reduce function, so that I get the grand total by summing the local sums over the processes. Note that in this case, I have added these two lines. I'm adding an explicit check that the number of processes actually does divide the number of elements in data. So the number of elements in data is hard-coded to 2520, but I'm checking that the modulo of the number of elements with the number of processes is 0. In other words, I'm checking, what I'm doing is, if it's not 0, then I'm aborting. Okay? So this Mpi Abort function will kill all processes in MPI.com world, and you will get this message that the number of elements is not divisible by the number of processes. So this basically allows you to run this program with any number of processes, provided that those processes divide. So it's not just fixed to 8 processes like it was in the previous exercises. Okay, so your to-dos are to implement the scatter operation here. So you need to put in the right elements here in order to estimate the correct number of elements that need to be scattered, etc. This local sum is already done for you here. Okay, so this is the sum over no local number of elements. And then you need to get the grand total by doing the reduction operation over the processes, so that you store the result in sum over the root process, right? And then at the end, the root process will write, I used so many processes, 8, and the sum is, you should get that sum actually, because we're using the same data.txt. So you should get exactly this number if you did it correctly. Good. So let's come back. I'll let you work on this, and we can come back at on the hour at 2 o'clock. Okay. Okay. So let's do this together. So the first thing we want to do is scatter. And we have here the array we want to copy into, the number of elements that the local copy should, the local part has. This is the big array where which holds all 2,520 elements, and 10 elements is the total number. So again, here we start with the send buffer, and then the number of elements that need to be sent to each process, remember, right? Not the total number of elements. So that's lock, the local one, the type. Okay. And now we need to put the receiving side. So that's vars lock. Again, elements lock. And MPI double. And then the root process, the process that holds the full array, is 0. And the communicator is our default standard communicator, MPI world. Okay, so now the array has been scattered into vars lock. Then each rank has a sum lock initialized to 0. This sum lock is accumulating each element of the local array. And now we reach this line here where we want to do the reduction over all processes, right? So sum over all processes. So Mpi Reduce. Let's look at the documentation. What do we need to do? So first is the send buffer, and the send buffer is, of course, the local sum, right? So that's what we want to send. Sum lock. And then where we want to put the result is the receive buffer, and that should be this sum here, right? Then comes the count. We only have one element we want to sum over. And then comes the type, MPI double, and the operation, which is a sum. The root process is where 0 is where the result will reside once done. And MPI world is the communicator. Let's see how I did. Submit the job script. And now, right, check the output, and this is consistent with what I had on the slide. That's the correct number. Now notice that this program has been written in a general way. I mean, I said that basically you just get the number of processes, you check if the number of processes indeed divides the number of elements, and if it does, then it continues. So the way this has been written, it should work for any nproc that actually divides the number of elements. And this number of elements has not been chosen randomly. So 2520 is actually, you can divide by several choices here. So let's see. So so had I wanted, if I want, I can use more processes to do this job. I just have to look at the submit script. So here it says end tasks 8, 2 nodes. So I can increase the number of tasks, for example, by going to 40, 20, is that? I think that's correct. Oops, 40. Yes, 40 does divide 2,520. So this will run 20 processes on each node. And it should give me an identical result. Whether it will be faster is not obvious because there's a lot of overhead in doing the initialization and the reduction, and this is a very short process. So, but if I had more work to do, probably I would see a larger speed up. In any case, I'm not really looking at the speed up now. I just want to demonstrate that indeed this can also work with 40 processes, giving me an identical result. See, used 40 processes, whereas before it said used 8 processes. Okay, and that shows a bit, yeah.
Can I ask the count argument in Mpi Reduce? Okay, we set it to 1, but
yeah,
what would happen if you set it to another number?
So it would, if you have more than one element here to sum. So if I go back to this picture, right? So here we just have some local. In this case, we have process 0 has some local, process 1 has some local, and process 2 has some local, and we want to sum these into just sum. But if what you wanted to do is add the elements of an array, like in the picture where you have array 0, 1, array 0, 1, array 0, 1, and you want to have, in the end, an array with 2 elements, and each element is the sum of that element over the processes, then you would have something here which would not be 1, would be the number of elements in the arrays. Okay.
Okay, thanks.
Right. Yeah. So this, oops. So that demonstrates. No, not that. Right. Yeah, I don't know. So if you want, you can try this using more processes to run it and convince yourselves that it works in general. For any number of processes, it divides 2,520. Okay, so this brings us to the end of this part, which is about collective operations. And so now I want to talk about point-to-point operations and MPI send and MPI receive. And for that, I'll step back in slides to the introduction. Just a minute. So yeah, so, oh no, I want to go even further back. All right, here we are. So the slide that says 21 out of 57 here. I'll make it full screen for a second. So point-to-point communication is any communication that involves transfer of data between 2 processes, okay? So far we've been seeing collective operations in which all processes had to be involved in calling the collective operation function, whereas here we can, the communication is just between pairs. Most common case, and the one we will see here, is a so-called send-receive operation, where one process is the sender and issues a send operation, and the other process is the receiver and posts the receive operation, okay? So you need to have 2 functions, 2 matching functions being called, one on the receiver, one on the sender. And these operations are very synchronous in nature, so you need to be careful when you use this for preventing deadlocks. So that means you know, reaching points in the program where the program can never finish. Deadlocks can occur when, for example, a process sends to another process which has not called a matching receive operation, or a process calls a receive operation, but there is no matching send operation, okay? So yeah, so that's just a very simple picture. You have, in this case, we have 4 processes, process 0, 1, 2, and 3. And in one case, process 0 sends this 4-element array to process 1, which puts it in a 4-element R array, send array, receive array. Whereas in this case, you have process 3 sending to process 2. So if I were to ask you how many point-to-point communications are happening here, you should say 2 point-to-point communications are depicted here. So 1 point-to-point communication is between 0 and 1, and the other one is between 2 and 3. Right? So again, I want to make the distinction between point-to-point operations and collective operations, in which you can point-to-point operations are just between pairs. Okay, so let's look a bit at the functions that we will use. So this is the send and receive operations. You might have guessed that they look like this: MPI send and MPI receive. You specify arrays, the number of elements that you want to send, and their data type. And then in the send operation, you specify an integer, which is the rank of the destination. Whereas in the receive operation, you specify an integer, which is the rank of the of where the message came from, of the source. Okay. All right. So an additional thing you can use to distinguish between messages is a so-called tag. So this tag has to be matched at source, so at the sender and at the receiver for this communication to complete. Okay. So it's an additional integer you can use beyond the destination and source being matched. You can use a tag to distinguish between, let's say, multiple messages being sent at the same time. And then you specify the communicator as always. And you also specify in the receive operation a so-called status. And I'll say something about this. So note the need to specify either a source or destination rank, source and destination. And by the way, n in the MPI receive case, okay, specifies the maximum number of elements that can be received, okay? So you could have a message with a smaller number of elements matching a receive on the other side with a bigger number of elements here. So this n on the receiving side just specifies the maximum number that can be received. And as I said, the tag variable tags the message. In the receiving process, it must match what the sender specified if you want this. Otherwise, it will deadlock. You can use this special variable, MPI any tag, in place of tag on the receiver, which just means accept any message with any value for tag, as long as it comes from the specified source. And you can also specify MPI any source in MPI receive, which means accept data from any source. All right, so the status we won't be using in our case, right? So the status can, but its purpose is to query how many elements were eventually received in the MPI receive, okay? We will just not care about this. So we will just assume that the correct number of elements we were expecting have been sent to, have been read from MPI receive, and we will use the special variable MPI status ignore here, which just means don't bother about the status. Okay, so
in which case would the n in MPI receive not match the number of elements that are sent?
So you can, so this n here in MPI receive is just the maximum. So you can use this operation, you can specify a number of elements to receive here, which is larger than the number of elements eventually received.
Okay, but why do we need to care about the maximum? I mean, in which cases would that be useful to have something else, or like something a smaller
Oh,
value?
I mean, you might, so the number of data to be sent might be determined at runtime, and you might not necessarily know how many elements, it might be computed on the sender side. So you might be doing something where you don't really know from beforehand what the number of elements you want to send to the other process is. You start your program, you compute it. So then on the receiving side, all you have to do is specify a maximum and then query the status to actually figure out eventually how many elements were sent, right? So it saves you sending an additional message from the sender to say how many elements it's going to send. It sort of saves you from that additional. Yeah. We won't be looking at any specific examples where we do this, but I can imagine a situation like that.
Thanks.
Right, so here's a very trivial example of send and receive. So you have process I wants to send this 4-element array to process J. Then you would have something like this in your code. So you, of course, will get the rank. You will call MPI-com rank and MPI-com size, etc. All the initialization stuff that you all know well by now. And then at some point you will say something like, if my rank is I, then do this MPI send to J, and the tag is 0. This is the tag that I just set to 0. And then on if my rank is J, I need to call an MPI receive. I need to call a receive array, 4 elements, double. And then the source the source rank is I, and accept any tag and ignore the status. Okay. Good. So that's how you would trivially use MPI send and MPI receive. We have an example that we will see where this is done in a bit more of a detailed, let's say, way, not so simple. But okay, and the next one I want to talk about is situations such as this one that's depicted here. Okay. So it's very common in parallel applications to require that every process communicates with another process, right? So like a neighboring process. So imagine that you have, that all the processes have these two variables. They have an S var and an R var. And you want a communication that every process needs to call an MPI send, right? So because every process is sending something, and every process wants to call an MPI receive because they all need to receive something, right? Okay, so this will not work. So this is code that you should not use, right? So what am I doing here? I am calling MPI send to send the S var, and then immediately afterwards I'm calling MPI receive to receive the R var. So every process has to, as I said, do the sending, and every process has to do a receiving from the other rank. This will result in a deadlock because why is this a deadlock? So the MPI receive, which is in the second line, can only be posted once the MPI send completes, but the MPI send will only complete if a matching MPI receive is posted. So all ranks will get stuck in the send because none of them will have a matching receive. Okay. So you could serialize the communications, like use a loop to determine the order of the send receives, etc. But that's not very practical. Serializes the communication that could, in principle, be done faster in parallel, and it's elegant, it's obscure and error prone. So that's why we have this function send receive, which basically does this, but sort of in a way that one is done on one thread and the other is done on another thread. And so they're done basically asynchronously. So MPI send receive takes basically the same arguments as a send, and a receive. There's all the same stuff, the send tags, receive tags, the communicator, and the status of the receive operation. So for the example that I'm showing above, then one would do something like this. So it's a scalar double precision variable, which we want to send to the next rank. And then we want to receive it in a double precision variable coming from the previous rank. So we always need to specify a send tag here, but the receive tag can be MPI tag. Okay, so what I've not done here is treat the edges in a special way, but maybe you can be imaginative and think. So this will not really work when rank is 0, because then this becomes a -1 and there is no rank with -1, and it won't work when rank is the last rank, because then rank +1 doesn't exist. So really what I should have done here is some more complicated arithmetic to handle the edge cases, but it will look something like this. If you let's say you had an infinite number of processes, then it would be this. Okay, so we will look at some examples of MPI send, MPI receive, and MPI send receive in exercise 7 and 8. But before I do that, I want to just talk a bit about some additional notes on variants of these point-to-point communications that we've covered, that we won't see examples of. Okay, just so that you know, just to keep in mind, maybe they solve a problem for you if you come up to it. So first of all, there are the variants with an I in front, MPI-I send and MPI-I receive. These are called non-blocking variants because the I stands for immediate, and immediate means that these functions return immediately. So they don't block waiting for either the send buffer in the case of MPI-I send to be sent, or the receive buffer for the case of MPI-I receive to be received. And then you use another function which is called MPI wait after you call these functions in order to block until the operation has completed. Okay, so you would do something like this, where you have MPI-I send, you have some arguments here, and then the last argument is the so-called MPI request. And then you can do stuff here. You can, for example, call MPI receive in here. You can do other things. But what you should assume is that between this MPI send and this MPI wait, this send buffer might be over the network, might be read from memory on the process. You should not do anything to modify send buffer because you might corrupt the message. So just because MPI-I send has returned, it doesn't mean that the buffer has been sent, but it's sort of being sent in the background, right? And you cannot be sure about which stage this send is. When you call this MPI wait, where this request is matched here, that's where the system basically checks whether this send buffer has been sent, and basically you block here until that message has been sent, and once you can continue after the MPI wait, it means that it's safe to modify the buffer again. Another variant that we won't cover, but maybe it's worth mentioning, is the so-called MPI send receive replace function, which is like MPI send receive, but with a single buffer rather than a separate send buffer in the receive buffer. So in this case, the receive message overrides the send message. That might be useful for you if you want to just have one buffer and not separate send and receive buffers. Okay, so I went a bit fast, but I think now is a good time to stop since there's a break at 2:30. Is that correct? I think
yes,
this is supposed to be, yeah. So I can stop now, and then we can we can look at the exercises, the two exercises of exercise 7 and 8 after the break. Should we keep the break at 30 minutes or should we make it 35? I don't know.
Let's keep it 35, so people join again at 3 o'clock, please. Okay. But we start at 3 o'clock sharp.
Yes.
Thank you.
All right.